All right, so here's the deal. Same thing as before. I will do my best to report everything as accurately as possible. This is working from my memory, so there could be some mistakes. Although in general, like dark energy, I'm even more familiar with than most other things. So let us get started with the discovery of dark energy and how this was done. Well, the discovery of dark energy, in order to understand what's going on, we have to understand how they made these measurements. So what they were looking for in particular, the astronomers were looking for, was a set of things that they could use as standard candles. So let me put this down where it belongs and make it the size that it's supposed to be. Like this. Okay, so standard candles. When we measure distances in the universe, it's built upon what's called the distance ladder. So let me get my cord out of the way. Distance ladder, that would be like this. Distance ladder, that's an L. Okay, so the distance ladder, that says distance ladder even though it doesn't look like it. So the distance ladder, basically what you're doing is, how do you measure distances from like the Earth? Here's the Earth, and you have some galaxy that's way out here. So here's some galaxy that's way off in the distance. How do we measure, how do we know how far away it is? Like, oh, this is 2.7 billion light years away. Well, we can't just do it directly, because the only way to measure distances on the Earth is to triangulate those distances. If you want to measure something, I guess you could do something where you bounce light off of it, you bounce a laser beam off of it, have it come back, and then record the travel time. That could also measure the distances. But if you want to do something where the light travel time is going to be really long, you have to use triangulation. You have to use geometry to do it. Well, there's no way to do geometry there's no triangle to form between the Earth and some distant galaxy. The size of the triangle that you would form here, so like here's the Earth, here's one side of the Earth and here's the other side of the Earth, for example, so this is the Earth. The triangle that you would form from the Earth to this distant galaxy has, the angle here is way, way, way too small to measure. And if you can't measure the angle, then you can't triangulate. You have to be able to measure the angle and kind of resolve it. And in fact, the size of the Earth isn't really big enough anyways. So what you do is you start by geometrically measuring the distances to the nearest stars. So that would look like this. And we exploit the fact that the sun, here's the sun right here, that the Earth has this orbit. So we can measure the positions of some star here relative to a bunch of background stars. So here's the background stars on the side. We can say, oh, when we observe the nearby star from the Earth, it appears here relative to the background sky. And when we measure, when the Earth is on the far side of the sun, or on the opposite side of the sun, the Earth, I guess, is never on the far side of the sun because we're always on the... anyway, so this nearby star will appear in two different locations in the sky. These locations are going to be very small, but that gives you this angle right here that is a parallax angle, usually given by the letter alpha. So parallax angle, if you measure this angle in arc seconds, so you have 1 degree is equal to 60 arc minutes, which is equal to 3,600 arc seconds. So if you measure this angle alpha in arc seconds, then what you get is a simple relationship. Because the angle is so small, you get the simple relationship that the distance is equal to 1 over alpha in parsecs. Okay, so a parsec is a length, not a unit of time. So with the Kessel Run notwithstanding, it is a unit of length. I think they had to go back and kind of rewrite the canon to make sure that Han Solo was actually using parsec correctly. So distance in parsecs is 1 over this parallax angle, which is at 1 arc second, you get 1 parsec, which is about, what, like 3 light years? Just over 3 light years for 1 parsec. So this is how you triangulate the distances to nearby stars. Turns out that no stars are within a parsec of the sun, and even to get to the nearest star, it's an angle that is smaller than 1 arc second, which is smaller than 1/3600th of 1 degree. So you have to have the ability to measure very, very precise angles in order to do that. Once you do that, you build up basically an understanding of the distances and properties of nearby stars. Once you've measured the distance to a nearby star, you can measure its intrinsic brightness. So now we have catalog. At the time, it was a catalog of, it was the Hipparchus catalog, so I guess Hipparchus, that was the one that was existing. This is from the early 90s, I think. And that was something on the order of 100,000 stars. So we'd measured the distance to 100,000 stars. Then we take those 100,000 stars and we plot their properties, and we determine, okay, here's how stars look in terms of like their brightness. This is brightness and temperature. And we know their distance, so we know intrinsically how bright they are, not just how bright they appear, but how bright they would be if they were at a fixed location. Can humans survive a hyperjump? I don't know what a hyperjump is, so I'm going to go with no. I would personally not care to partake in a hyperjump. So you measure, Hipparchus measured these 100,000 stars and tracked their properties versus, basically their properties as a function of how far away they are. That allows us to make models of how stars shine. So this information, the Hipparchus information, goes into stellar models. So now we understand basically how stars shine, and we can say, oh, now I'm looking way off in the distance to a star that I cannot measure the distance to, but I understand its properties. So I measure a distant star and it lands like right here, and that corresponds to a specific stellar type. I can model that star. I can determine its intrinsic brightness as a consequence of that. In particular, what was discovered and was most useful was a set of stars that actually, in this particular diagram, kind of live up in this area. These are called horizontal branch stars. So these are stars that pulsate, or Cepheid variable stars. There's a variety of variable stars. Variable stars live in a column on this particular plot that's like this. So variable stars are unstable in that they have a phase transition that happens when the star compresses. It heats up, ionizes a layer, and that builds up a bunch of pressure inside from the radiation trying to get out, and then it causes the star to expand, and then it cools off, and that layer deionizes, and then it shrinks back down again until it ionizes again. And then it gets, so you have this pulsation that's driven. The pulsation properties, like the rate at which it pulsates, is related to the intrinsic brightness of that star. We can measure basically how bright a star is by looking at its pulsation frequency, and that was determined by looking at these nearby stars and determining the mass or the luminosity relationship that you get from that. Okay, so these horizontal branch stars are actually pretty bright, and it was Edwin Hubble that discovered horizontal branch stars in the Andromeda Galaxy. So we have the Andromeda Galaxy. If I pull up Edwin Hubble var ! So there's a very famous image, very famous amongst the 100 people that know about it. Everyone should view it, imagine it as famous. I think this was, we've already seen it once in the astronomy picture of the day, but now we're going to see it again. It is this figure. So this is the Andromeda Galaxy, as observed by Edwin Hubble. And he shows right here, there's a star in that location, star in this location right there, that one right there. And he marks it, and he's like, var! ! So that means he discovered a variable star, a Cepheid variable star in this location, tracking it over the course of, over a period of time. He was watching how the star fluctuates in brightness. The frequency with which that brightness fluctuation happens tells him the intrinsic brightness. That intrinsic brightness was discovered or figured out by mapping out the properties of the nearby stars. So Hubble was able to establish from the intrinsic brightness of that star, relate it to how bright it appeared, and then get the distance to the Andromeda Galaxy, which turned out to be very, very far away. So then, from there, he took, that gives him the distance to the Andromeda Galaxy. So then you start constructing other ways of, so now you have the brightest stars, but that can kind of only get you to nearby galaxies. Then you have to come up with other ways of determining distance. So you say, okay, well, I've got the geometric measurements. That gives me stellar measurements. That gives me horizontal branch star measurements, or like variable star measurements. Variable star measurements can get me to different galaxies. And then you can start looking at other properties of galaxies. For example, you can have H2 regions in a galaxy. So if we look at H2 region, an H2 region in a galaxy looks like, well, there's basically bright pink regions. Is it H2 region? I'm pretty sure it's H2 regions. It might be H1 regions. Let me try. Let me see what H1 regions look like. Anyways, there's these bright cloudy regions. H1 region. This isn't the kind of stuff that I study because I just don't. Let's see if H1, interstellar medium control, neutral atomic. So it wouldn't be that. So it is going to be H2 regions. I was right the first time. H2 regions. So you look at H2 regions in a galaxy and they appear to be bright. So they're bright clouds in distant galaxies. And they tend to come in kind of comparable sizes. So in a distant galaxy, which actually means a really close galaxy, you would look at these H2 regions. So for example, here, if we look at this galaxy, these H2 regions, it's these clouds, these pinkish clouds along here. So you can basically say, what is the distribution of brightness of these pink clouds? And then, because those you can see farther away, they're brighter than individual stars. And then you can say, okay, I know how bright those things are in the Milky Way galaxy and in the Andromeda galaxy. And so I can see how bright they are here, and that gives me the distance to these kind of intermediate galaxies. But then you run into problems. How do you get distances to really, really distant galaxies? And so what you need are things called standard candles. Standard is spelled like this, standard candle. So a standard candle is some astronomical object that where you know its intrinsic brightness. The brighter the object is, like the brighter it shines, the more distant you can measure these things. So finding a standard candle was a challenge and has always been a challenge. And the more standard candles we have, the better we can constrain the history of the universe. So one of the standard candles that came up was type 1a supernova. So that says supernova. Type 1a supernova. So these are stars that are exploding white dwarfs. So you have a white dwarf. White dwarfs reach a certain mass that happens to be 1.4 solar masses. When white dwarfs reach 1.4 solar masses, they become unstable and they explode in a large explosion. These large explosions release huge amounts of energy. So a single white dwarf, like a type 1a supernova. So this is a type 1a supernova. It's type 1 because it's missing certain spectral lines, and it's a A because there's other classifications. Type 1a is these exploding white dwarfs. They all happen at the same mass. They all happen at roughly the same composition, right? So these are going to be mostly made out of carbon and oxygen. That's the bulk of their composition because it's a carbon-oxygen white dwarf. So they have roughly the same material. They have essentially the same mass when they explode. And then these things explode and produce a whole bunch of material. So a white dwarf blows up. Here's the white dwarf. It blows up. It sends out a bunch of radiation. So you have a bunch of photons that come out. A single exploding white dwarf will outshine hundreds of billions of stars for a brief period of time, but it does outshine hundreds of billions of stars. And it also gives off a bunch of particles. It gives off neutrinos, for example. So this is a photon. It doesn't look like a photon maybe, but that is the chemical symbol for photon. This is the chemical symbol for neutrino. Of course, the neutrinos would be going straight. The photons would be wiggling. Okay, so you're sending off all this stuff, a bunch of particles. It turns out that 1% of the energy comes off in photons. 99% of the energy comes off in particles, including neutrinos. This 1% of the energy outshines 100 billion stars. And so this is like, what, 10 trillion stars worth of energy is coming off in the form of high energy particles. So that's pretty gnarly. These type 1a supernova, because they all happen at the same mass and they all happen with similar composition, they are a good standard candle. Now, there's a caveat next to this. They themselves are not intrinsically standard candles. And so the practitioners of the field have often, though I don't know if this is a generic term or like an accepted term, but I have often heard it referred to as standardizable candles. So what happens is you have the supernova blow up. So here is T equals 0, and these supernova, they explode, they get brighter for a period of time as all the light escapes out. And then a bunch of processes take over that are kind of interesting, and then they decay over time as well. So this is the brightness, bright, that says bright as a function of time. From the explosion, you get this thing, the light comes off, it gets bright for a period of time, It peaks at something around a month, and then it decays after that. So 99%, it's not all cosmic rays. So cosmic rays, when you have one of these stellar explosions, a lot of it is particles. Neutrinos aren't really cosmic rays the way we think of cosmic rays, because neutrinos' probability of interacting with the atmosphere is so small. Cosmic rays are basically usually iron or like protons, like some nucleus that's streaming through the galaxy that then when it hits the upper atmosphere creates the cosmic ray showers. So most cosmic rays that we can detect are going to be nuclei that are streaming through. Okay, so it's about a month and then it decays. This profile here is actually dominated by a radioactive alloy, a radioactive isotope of nickel. It's nickel 56, I believe. So nickel 56 is radioactive. We can verify this real quick. I believe the time scale of its radioactivity is something on the order of a month. So let's look up nickel 56. Everybody's favorite isotope of nickel. Nickel 56, it is not nickel 50. Oh, nickel 56 is not listed here, which implies that it is unstable. So those are the main isotopes of nickel. We're looking for the not main isotope of nickel, which has a half-life of 6 days. Okay, so 6 days. So the peak of the brightness of the supernova is going to be, like the first 6 days is going to climb as the nickel 56 starts to decay. So there are other things that are produced that have half-lives at other times. Okay, so the millisecond one, nickel 55, that decays in a millisecond, that's not really important. But you are going to produce a variety of isotopes, and the long-lived ones are going to be the things that contribute, as they decay, it's going to contribute to the light that comes from these type 1a supernova explosions. Now, let's take a look and see what these type 1a supernova explosions look like. Type 1a supernova. Type 1a supernova. This is an artist's impression, and we don't want to look at that. We want to look at an actual supernova. Here is this, that's the spectrum. We don't want to look at the spectrum. We want to look at, not that, not these. Oh, so these are computer simulations about how they explode. And for a long time, this is a fairly recent result, actually getting computer simulations of type 1a supernovas to actually explode instead of starting to explode and then collapsing on themselves. Let's see, not seeing very many pictures here. Okay, here is this luminosity relationship. So this is what I mentioned. The plot of luminosity relative to the sun versus time shows, here's the peak at nickel. So I was wrong when I said a month. It's actually more like 6 days, but it has a tail that stretches out. So 6 days to here, and then you can see that the tail stretches off, for about a month. And then cobalt. So nickel is the thing that drives the brightness initially, and then cobalt is the thing that follows. So there's two radioactive isotopes that are produced in the explosion itself. Not seeing, so we're going to go back to the type 1a supernova and look up images, because that's what we want to see. This is a really famous image of a type 1a supernova explosion, and so we will use it. So here's the galaxy. The galaxy has a disk. That disk has lots of dust in it. That's what these dust bands are. And then right here, this is a star that's in the halo of this galaxy that just underwent a type 1a supernova. So type 1a supernova goes off, and you can see that this star, it might not be as bright as all of the galaxy here, but this is a single star that's actually just not much bigger than the sun. A single star that's outshining however many hundreds of millions of stars there are in the center of this galaxy. And this isn't necessarily at the peak brightness either. So this is a demonstration like how bright these things are. So if you can see this galaxy, then you can see a supernova going off in that galaxy. That's the important thing, is that these type 1a supernova, because they all have the same, well, because of how bright they are, if you can see a galaxy, you can see a type 1a supernova in that galaxy, which means no matter how far away the galaxy is, you should be able to identify the distance to that galaxy if you can detect a type 1a supernova coming from that galaxy. So type 1a supernovas, they're not, well, speaking for the universe as a whole, they're pretty common. For our galaxy alone, they're fairly rare. It's like once a century that you get a supernova. But if it's once a century, then that means that if you look at 100 galaxies, then you'll get once every year. And if you look at 1,000 galaxies, you'll get a supernova every month. And if you look at 10,000 galaxies, then you get a supernova basically every day. So by having a large survey of galaxies, you can accumulate detections of these type 1a supernova. And we know that because the supernova are all the same mass and all the same composition, they are essentially the same brightness. What actually happens is you get a family of curves. So here is the brightness, and they don't actually, at least as far as I remember, they don't actually know why these curves are all the way that they are. But basically you have a family of curves that are related to each other like this, and what you do is you detect a supernova and then you watch how bright that supernova is over time. So you're plotting the brightness of the supernova as a function of time, like this. Okay, so like you finally detect it and then you watch how it decays, and then you measure the width of this, and they call it the stretch. So what's the stretch of the light curve that you have from this supernova? When was our galaxy's last supernova? So there's supernova 1987A, which was in a neighboring galaxy. The last one that I can think of is like Tycho Brahe's, is it Tycho's supernova or Kepler supernova, like 1604, something like that. So that's all that I can remember. Thank you for that raid. I appreciate that. Thank you very much. I appreciate that raid. So we're talking dark energy today. For those who are just joining, my name is Jason Steffen. I'm a physics professor at the University of Nevada, Las Vegas, and we're talking about the discovery of dark energy. Okay, so the stretch. The stretch is basically the width of this light curve, how long it takes, to trace out, how long it takes to grow and shrink again in brightness. And then that stretch happens to be, once you correct for that stretch, you can get the intrinsic brightness. So if you stretch it out by some amount, then that fixes the intrinsic brightness. So now you have a way of getting the intrinsic brightness of these supernova explosions, and we've seen here that those supernova explosions can be detected at great distances. Now you have a way of measuring some of the properties of the universe. So let's talk about how this is going to work. Normally when you have a standard candle, a standard candle is an object where you know its intrinsic brightness. So here is like a light bulb, a 100-watt light bulb. It looks like a 100-watt light bulb, I'm sure. Okay, so this is 100 watts. Okay, and then here is your detector over here. That's you detecting it with your spyglass. It gives off 100 watts. If you know intrinsically that it's 100 watts, then as the light propagates over some distance, it's going to spread out because it's 100 watts going through any concentric sphere as you come out. If you go out some distance, you're not going to detect 100 watts. It's going to be 100 watts across the entire surface area of that sphere. And so the amount that you detect crossing some threshold, like some size of your aperture, is going to be 100 watts divided by or multiplied by the ratio of the area here compared to the area of a sphere. The point being that the light's going to spread out, and the light is going to become less and less intense as 1 over r squared. The reason it's 1 over r squared is because the total energy is conserved. Total energy is conserved, and that energy has to cross a surface area. So you have a surface area, and you have to multiply that by the distance, and surface area goes as r squared. Right, surface area goes as r squared, which means that the intensity has to fall as r squared, so that when you multiply the surface area times the intensity, the r squareds drop out. So it's a total amount of 100 watts going through any surface of a given size, and that has to drop out. The fact that the surface area of a sphere is getting larger the further the distance is, means that when you multiply intensity, which is watts per square meter, times the surface area, that intensity is watts per square meter, which gives you an r squared, and the surface area is 4 pi r squared. The r squared drops out and you get a constant, and energy is conserved, and so it must be a constant. So that's the thing. Light has this property where as it spreads out, the intensity of the light falls as 1 over the distance squared. So that's when you measure the brightness of an object like a light bulb, and you say, oh, I'm only getting 1 watt per square meter here, then that implies that you are 10 meters away from the light bulb because it's fallen by a factor of 100, and you have 10 meters away, which means that the light has expanded out by, the surface area that it has to go through has expanded out by a factor of 100. Okay, so you can measure how bright the thing appears and compare it to how bright it is intrinsically, and that will get you the distance. We know that in this case it was 10 meters. So the same thing happens with distant supernova. So here's a galaxy. This is a galaxy off in the distance. It has a supernova that goes off. Here's the bright supernova. It's giving off light. And then here's you with your telescope now. And you're looking at the brightness of that object. And you can measure, as a consequence, because you know its intrinsic brightness once you correct for the stretch. Once you know its intrinsic brightness, that can get you the distance. It's called the luminosity distance. Luminosity distance to that galaxy. So the luminosity distance. Now, why is it called the luminosity distance? That's a great question. I'm glad that I asked it. So the luminosity distance is the distance that you get from this property that light gets less intense as 1 over r squared. So you assume that the intensity of light falls as 1 over r squared, and then you know its intrinsic brightness, and so you can calculate the luminosity distance right there. That would be this r, that distance is the luminosity distance. It's not the Illuminati distance, it's the luminosity distance. Okay, so that is the luminosity distance. Now that you have these type 1a supernova, you can get the luminosity distance to different galaxies, and there are lots of galaxies where they measure these distances. So let me show you an example. The Sloan Digital Sky Survey did a supernova survey looking for these different things. So if we go SDS Supernova Collage, not college, collage, this is a fairly famous image. Where is it? Where's the image? It's gone. SDS type 1a. Here we go, this one. Oh, this is that's the one right there. Is it going to show me the whole thing or just part of it? Okay, well, we'll use this one. Okay, so this is an example of a Sloan Digital Sky Survey Supernova Collage. All right, you have a distant galaxy, and you can see that each of these galaxies has a bright blue spot. That bright blue spot is the supernova. The galaxy is the smudge. So the smudgy stuff is a galaxy. The bright blue spot, or white colored spot, is, so here's a galaxy, there's a supernova. Here's a galaxy, the supernova is actually in there. Here's a galaxy, there's a supernova. Here's another galaxy, there is a supernova. So those are all the supernova that were measured by the Sloan Digital Sky Survey, and they go back and measure it repeatedly in order to trace out the light curve, which then allows them to measure the stretch, which then allows them to measure the luminosity distance. So now they have distances to these different galaxies. Okay, now, once you have this luminosity distance, you can compare the redshift, because Hubble discovered back in the day that galaxies are moving apart from each other. Basically, you have all these objects and they're all spreading apart from each other because everything is spreading apart from everything else. And that means that the galaxies are kind of drifting through space as space expands between them. All right, what does that imply? That implies that the farther away an object is, so if we consider, for example, here is a rubber band with 3 dots. We're going to do a rubber band with 3 dots on it. Okay, and in a given period of time, we're going to stretch that rubber band to a large distance like this. So now we have there, and here's the middle one, and here's the one on the end. Now, if we're standing here, if this is us, and everything is spreading apart uniformly because it's a nice, continuous, homogeneous rubber band, so there's no density variations in it, in the same amount of time that it took for the whole rubber band to stretch, this point has gone twice as far as this one. So in the same amount of time, it's gone twice as far, which means that objects that are farther away are going to be moving faster. Because it's twice as far, in the same amount of time, it has to have twice the speed. And so as the universe expands, things that are nearby are going to move at slower speeds, and things that are farther away are going to appear to move at faster speeds. They drift. Well, space stretches. They're not necessarily drifting through space. There is some of that, but that's not what's really going on. It's the space between them is stretching out, and they are being dragged along in space with it. So that's basically the Hubble law, is that nearby objects move at slower speeds and distant objects move at faster speeds. So when you have a galaxy that is moving away from you, you can measure its speed. It's actually fairly easy to do, to measure its speed. If we look at a galaxy spectrum, let me pull up here and pull up a galaxy spectrum. Galaxy spectrum. So this is what galaxy spectra look like. So I'll steal this image. Okay, so here's a spectrum from a galaxy. You have some emission lines. So this is H alpha emission line. I can zoom it in even a little bit more so that it's even more amazinger. So this is the flux in 10 to the minus 17 ergs per second per square centimeter per angstrom. Okay, so for all those who really care about the units, this is basically how bright it is at these different wavelengths. So here's H alpha, that's a hydrogen emission line. And then you have a bunch of other things like H and K Fraunhofer lines, that's iron. Here's O2, that's an oxygen emission line. So you have all these features, and we know what these features are. Here's H beta. So H alpha is here, H beta is right there. So we know what these features are. So when you see this distant galaxy, you can look at the spectrum of light coming from that galaxy, and you can compare it to where that feature would appear in a laboratory. So if it appears in a laboratory at, say, 5,000 angstroms, nobody uses angstroms anymore. You can tell that these are cosmologists using angstroms. So at 500 nanometers, 5,000 angstroms, if this line were supposed to be, if there was a line that's supposed to be at 5,000 angstroms, and instead you measure it at 6,000 angstroms, then that implies that that light has been stretched out, which gives you how fast that object is receding from us. It gives through the Doppler shift, basically. You use the Doppler formula. So it tells you how fast that thing is spreading out. Use the relativistic Doppler formula. How fast that thing is, how fast it's moving away from you, which tells you the redshift. And because the farther away an object is, the faster it's going to be moving. That gives you a second measure of the distance. So we now have two different measurements of the distance. One of them is that you get from the redshift, how much the light has been stretched out, which you can get from looking at the spectrum. And the second one is the luminosity distance that you get from the type 1a supernova. Now, the way that they do these with the big surveys is they don't always do spectroscopic redshifts like this, where they take the spectrum. For example, with the dark energy camera that is operating dark energy survey that has the dark energy camera on it, they don't do spectroscopic measurements. So they don't take the light and shine it through a prism and break it up into all these wavelengths. Instead, they do what's called photometric redshifts, where they just take, they're looking at the red edge. I think that's what it's called, the red edge. So here's another galaxy spectrum. There's this edge, you have a kind of a sharp edge right here. And so what they'll do is they'll take how bright the object is in this passband, like at these wavelengths, and how bright the object is at these wavelengths. And as the galaxy is redshifted, as it moves away from you, the faster it's moving away from you, the more redshifted it is. This edge will pass from one observation band, from one region in color to a different region in color. And so by looking at where does that transition, the abrupt transition have between where it's super bright and where it's less bright, that gives you another handle on the redshift. It's not as accurate as a spectroscopic redshift where you actually resolve the features and then compare it, but it's good enough if you need to do hundreds of thousands of galaxies and you don't have the time, or millions of galaxies. Instead of like taking individual spectra, you can take spectra directly from the photographs by using different colors to filter it out. So the point being that you measure the redshift to these galaxies. So now you have two different measurements, and you can compare the brightness that you get, or the luminosity distance, the brightness that you would infer from the supernova, with the redshift, which tells you how much it's been moving through the Hubble flow. So redshift implies speed, yes. So this redshifting implies a speed with which the object is receding from us. It's a little bit different here because in this case it's space that is expanding, and you have light that's traveling through that space, and as it travels through the space is expanding and stretching out the light itself. So it's not exactly analogous. It's analogous enough to the Doppler shift that it's, that's the method that's the language that we use to describe it. And I say we, I'm invoking all of the other cosmologists, but it's actually a gravitational. It's related to the stretching of space-time, and you have a photon that's in there, and as space-time stretches, it stretches the photon out. So it's a little bit different. For one thing, the Doppler formula, the original Doppler formula, doesn't go beyond the speed of light, but the speed of light in a vacuum is the limit on how fast light can travel through space. It is not a limit on how fast space itself can expand, or the space between two objects can expand. And so you have redshifts that are larger than 1, which means that these things are receding from us faster than, well, really fast. And in some cases, you have objects that are receding from us faster than light can travel between us, and so they fall off of the horizon. Okay, so that is, we have these two measurements of distance, the redshift and the luminosity distance. Would we see a difference if what we saw was space being created rather than expanding? I think they're basically the same. They're two different ways of saying the same thing, that when the space between them is expanding, if you don't expand your coordinate system along with it, then that is creating new space. If you do expand your coordinate system along with the expansion of space, then you call them co-moving coordinates. But if you don't use co-moving coordinates and instead you use the meter, then when the space expands between them, it's creating more space. So it kind of depends on your unit system. All right. So that gets us to, we now have two different measurements. And here is where the gnarliness comes into play. So we have the redshift, which gives us one measurement of the distance between us and our observed target. And we have the luminosity distance, which is another way of measuring distance. Now, if space is expanding uniformly and constantly in all directions, like this, in some kind of is drifting at a constant speed, then the luminosity distance would scale as 1 over the separation squared, like 1 over the expansion factor squared, how much the universe is expanded. However, if the universe is evolving, so let's say that you have a bunch of mass in the universe, that there's matter. For some reason, there's a bunch of matter in the universe, which we still don't know why, but we have a bunch of matter in the universe. That matter is going to cause things to kind of come back together again. Gravity is going to slow down the expansion. So you're going to have the influence of gravity in the universe, which is not going to give you this kind of expansion, but is instead going to give you some expansion that looks like this. Okay, because gravity is pulling everything together. If there's a lot of gravity, if there's a lot of mass that pulls a lot of things together, you can eventually have all this stuff recombine. Okay, so what's going to happen if you measure a supernova where the universe has expanded outwards and then started to contract? So here's a supernova explosion, and here's the light coming off of that supernova explosion. Okay, so all of this is light. I'm trying to show it as like a potentially three-dimensional object, but I might not be doing a very good job at it. And so here's you looking at it with your telescope. You see this distant explosion. When there's not much happening, like early on, it is following this. The luminosity falls as 1 over. It's the intensity that falls. The intensity falls as 1 over r squared. However, if the universe starts to contract, then it's actually going to start bringing this light back in and focusing it again. It's going to pull the light back inwards and start concentrating that light, which means that the intensity is going to rise again. So at a certain distance, the intensity will be larger than it was otherwise. So if you're standing right here, the intensity might fall as 1 over r squared. But if you're back here, that 1 over r squared pattern is going to break, and you're going to get some different pattern. So if you look at different supernova at different distances, you can trace the overall history of the universe in terms of, was it expanding for a period of time? Did it start to contract? Did it expand again? Did it contract again? You could imagine a situation where you have the universe as a history went through a series of phases where it was just like expanding and contracting for whatever reason. There's some, it's like an accordion, and the Greek gods are playing this accordion, and the universe is expanding and contracting again. And so a supernova that goes off in a given place, the brightness is going to wiggle around like this. So here's the brightness of that supernova, or the light coming from that supernova. And so if you're standing here, you're going to observe that distance, and you're going to compare it to some luminosity distance. But then when you're at this distance, which is a different redshift, so the redshift is different, but the light's going to be concentrated. And then here the light's going to be diffused again, and then it's going to be concentrated again. Yeah, so it's like the gods' polka music as they're doing this. So by comparing the redshift that we measure, which gives us kind of the drift, the distance equals rate time times distance. So when you measure a redshift, you get a velocity, the recession velocity, and you compare that to the Hubble constant. So it's like what the velocity, the receding velocity is h times L, right? I think that's right. Let me look it up real quick just to make sure you can see how often I teach this. So I want the Hubble law. L, D, whatever. So D is the distance, H is Hubble constant, and V is the recession velocity. So you can get the distance, so this is the distance. So now it's a D. Okay, so you can get the distance by measuring the Hubble constant. So that was, that you can do. And comparing it to the recession velocity. You divide those two, that gives you the distance. So you have the Hubble distance, the distance you get from the Hubble law, and you get the luminosity distance. And you can use those to compare and look at the history of the expansion and contraction of the universe. Okay, so then what do we find? That's where the question comes in, is what do we find when we do this? Turns out that when you map these, okay, where is it? I pulled it up. Here it is. This is observational evidence from supernova for an accelerating universe and cosmological constant. You'll notice two of the lead authors here. Oh wow, I didn't know that he was on there. Adam Rees, Nobel laureate. Alex Filippenko, also a Nobel laureate, for this paper. It's this paper that they did. Observational evidence from supernova for an accelerating universe and a cosmological constant. Let's see, so this has 13,000 citations. That's a lot of citations. 13,000 citations is, thank you for that, Raid, I appreciate that, is a lot of citations. I don't have any papers that have 13,000 citations. Let's see, who do I know? So I know both of them. I know Ron Gilliland. He's a stellar astrophysicist. Craig Hogan is and Chris Stubbs. So he was at the University of Washington. Craig Hogan at the time was at the University of Washington, although they're both now, Craig Hogan is at Fermilab and Chris Stubbs is at Harvard. Ron Gilliland retired. So anyways, there's a bunch of people on here that were studying these distant supernovae. So let's go down, it's 36 journal pages, that's a lot. Let us go to graphics. Okay, so they make these measurements. Here is, let's see, do we want high resolution? These are kind of, all right, so these are the days. Here you can see them tracing out. This is what I mentioned before. This is the brightness. This is the brightness in the B band. This is the brightness in the visible band. The brightness of those supernovae. Notice that they're not exactly identical to each other, but they are able to stretch out, but they put them on these stretches, these deltas right here. Give you the stretch to calibrate the supernova and therefore get the luminosity distance. So that is that figure. This is them calibrating the supernova to get brighter is a slower decline. That's this stretch up here. Dimmer is a faster decline. That's related to the details of the composition. Okay, then they made this. So here's a variety of supernova. Okay, and the redshift. They measured the redshift by taking spectra of the different stars. This is in the 1990s. Okay, so there are different supernova measurements. And then it's this figure right here. This is the figure that won the Nobel Prize. Oh, that's cool. Chris Stubbs wrote a paper about octopus vision. Okay, so here they are comparing different predictions for what the expansion of the universe would be, like what the history of the universe, the expansion and contraction history of the universe would be with different cosmological parameters. These cosmological parameters for the moment are not that important. And they're basically saying, here are the data that we get. So this is the brightness of the observations that we get as a function of redshift, right? Here's redshift down here, it's given by Z. So that's redshift out to redshift 1. So they make these measurements and they plot them on this line. And the question is, which universe is most consistent with the data? They have a matter-only universe, that's this line here. They have a critical density universe. This one, the one here in the middle with a dash line, that's the one that they're comparing it to, because this is roughly what you would expect for a universe. So they have two parameters basically that give them these different curves. Two parameters give them these different curves, and then they need to ask the question, which one is most consistent with the observations that we make? And you can see from this that as they get out to larger and larger redshifts, that's where the distinction comes in. So the farther out you go in redshift, at least up to a point, farther out you go in redshift, the better you can distinguish between these different cosmological models. Like how much matter is there in the universe and how much other stuff is there in the universe. And they found that as they got out to more and more distant redshifts, the data were clustering above this dotted line, which implies the presence, and that's what's shown here, it implies the presence of this lambda, this omega lambda quantity. So these other ones, if I get out of the way, have no omega lambda. They have some matter, but not omega lambda. And basically what they're saying is if omega matter, these things have to sum to some value. Well, I guess they don't have to sum to any particular value, but now they do because there's corroborating evidence from other measurements. So they said if the universe is filled with matter, that would be this one. That's inconsistent with the data. The universe is not completely filled with matter. There's something else there. What if it's just less matter? That's the second option here. If there's just less matter, then that would be the dotted line. And all of the points out here, or the majority of the points out here, they tend to cluster above the dotted line. Therefore, you can't just explain these observations with a matter universe only. So now we have to add in matter and omega lambda, which is dark energy, to add in dark energy, and that is the line, the solid line, and that's the one that's consistent with their measurements. It does look like a 3-year-old's drawing, and the distinction is not great, right? There's not a whole lot of difference between these, and so you have to make a lot of measurements, right? They had to make some, what looks like 30-ish measurements in order to do this, but the statistical significance rises with each new data point that you get and the precision with which you can measure those data points. And so it shows that as they get up to this further distance, to larger redshifts, like galaxies that are farther away, supernovae that are farther away, then the only way to really explain these observations here is to invoke the presence of dark energy. If we scroll down, they're showing here the ratio of where the data lie compared to a standard model, which is this dotted line in the middle. So that one, they're saying, what are the deviations that we observe from this one that we see in the middle? And this is what they get. And you can see that for low redshifts, so this is low redshift down here, they cluster kind of on both sides. It doesn't really distinguish very much to have a low redshift. But at high redshift, high-ish redshift, from 0.1 to 1, all of the data points, all except for one, basically cluster above that line, and therefore there must be some kind of dark energy, some kind of acceleration in the expansion of the universe. So basically what they discovered here was that the universe was accelerating in its expansion. These supernovae, the ones that are at large distances, are too dim. They're dimmer than what they should be. Basically what this shows is that back in the day, here was a supernova explosion and the universe was going like this, or has been going like this. And so it doesn't fall as 1 over r squared, it falls faster than 1 over r squared. So here's the observer out here. 1 over r squared would mean that the universe was spreading out like this and that the surface area was growing geometrically the way that we would think it would on a piece of paper. But because the universe is accelerating its expansion, the light is spreading out even more than otherwise, and so supernovas at this distance are even dimmer than they should be. And that was the thing that was the smoking gun for the acceleration in the expansion of the universe. You get enough data points and you can make this measurement. So this was the original claim. There was another group that was making different measurements using different supernova, because they weren't looking at the same supernova. They were observing their own sample of galaxies to get their own supernova. I think the group was out of Australia, and they published similar results. They came out basically at the same time. So this paper won the Nobel Prize. Let's see, what are these? These are the observations that constrain these cosmological parameters. And it shows, so here's omega matter, that's like regular matter in the universe. And then here's omega lambda, and these are their confidence intervals. And in particular, the important thing here is that these confidence intervals don't really overlap with 0. There's strong evidence that omega lambda, which is the dark energy, is non-zero. And they did it at, whatever, 2 sigma or something like that. Or it's probably a 3 sigma result. These are the confidence intervals, but then you have to integrate the total density across this thing and get what's the probability of this error ellipse, how much of this error ellipse is actually below 0, and you get a small number. So you have a large, most of the volume of this. So this error ellipse is a blob, is like a Gaussian of some height, and then you say, here's all these points with some probability. You integrate, or you add up all the probability across all these different ellipses, and you say, how much does that volume compare to the volume down here? And you get some ratio that indicates that you have a high confidence that you're measuring something that is non-zero. And it's basically been confirmed over and over and over again. They did have big error bars, right? These are the first measurements of this effect, and it did have fairly large error bars. However, we can look at subsequent measurements. So let's take a look at more recent measurements, like high Z supernova results. Let's see if there's more recent images that show. Okay, so that one we've seen. Here's more data. This is the combined. So the Supernova Cosmology Project was the other one. So the High Z Supernova Search Team, that's the one I think that we just saw. I believe the one we just saw. And the Supernova Cosmology Project is the other one. I could have those backwards. But when you combine them, so the two different teams together, again, it looks like they all clump up here, but again, you can see that they cluster above that line. They cluster in the region where everything above this line requires dark energy, basically. So this is the dark energy model, and that is favored by the fact that all these data, it's not that all of the data are above the line, but the bulk of the data are above the line with some statistical significance. There are more recent measurements that go out to higher supernova. Here's all the people that won the Nobel Prize. Where are more recent supernova results? Yeah, okay, so let's do SDS Supernova Results and see if I can find, if they have their measurements. This is not looking promising. Okay, here we go. This is what we're talking about. Ha! All right, this is a combination, it looks like, of a variety of different supernova surveys. It's a low resolution version, so you're gonna have to forgive me for that. So the nearby ones, that's these ones down here. Notice this redshift. So the High Z Supernova team went out to basically redshift 1. So some of these data points are out here. There's some from the Hubble Space Telescope that were observed. Those are in the distance. You have this supernova. This is Supernova Legacy Survey. That's this one. Essence, I don't remember where Essence came from. Supernova Legacy Survey, that I believe came from the Sloan Digital Sky Survey. SDSS2, so that's the ones that filled in this area. So they've made all these measurements from redshift to zero out to about redshift 1.6. I think they're getting now out to like redshift 2. And then you would compare these results. So this is a combination. You can see that it follows a nice curve, which means like when you're surveying these things, each of these surveys is in a different part of the sky, right? There's some are in the northern hemisphere, some are in the southern hemisphere, some are using Hubble and looking in arbitrary directions. And so you piece them all together, and it doesn't matter which way you look, you get a uniform distance modulus, right? That's the luminosity distance versus redshift. I wonder if I can find, it'd be nice if I could find one that actually showed the models going through there. We could go straight to the publisher website. Okay, let's I guess go to figures. Nah, not figures. Let's go straight to the article. It might be a long article, but we'll find the figures in here. It's 53 pages. Okay, we're going to go quickly through this to see if we can find the right figures. That's not it. These are not the figures that we are looking for. It's probably going to be at the end, because the first number of figures are all going to be like calibration type stuff. All right, these aren't really looking as promising as, okay, here we go. So this is like the combined, so let me zoom in here. These are like the combined measurements of a variety of things, right? This is Sloan Digital Sky Survey only, Sloan SDSS, Essence, and SNLS. Nearby plus, so they're adding all of these different surveys together, saying with Sloan Digital Sky Survey, this is saying like, The no dark energy model is the horizontal line. The dark energy model is their best fit model, is the one that goes above that line. And they have to combine them all together. So all these different measurements, there's always fuzz in your measurements because sometimes galaxies might be in a group of galaxies and they might be moving towards us, which gives you a redshift that's actually distorted somewhat because you have the Hubble drift, but you also have the peculiar velocities of the galaxies that they move around each other. So, but they add more and more data, and then they bin them up. They like say, well, the average of all these ones is that, the average of all these ones is this, the average of all these ones is this, and get those magenta points. And all those magenta points indicate that the universe actually has some dark energy. So ultimately what they got is that the universe is accelerating in its expansion and that there's some energy that's driving the acceleration. And that was the discovery of dark energy through these supernova measurements, and that won the Nobel Prize. So I hope that was interesting. I'm happy to answer any questions about it. Let's see. Dark energy must be real, but actually look at the data makes me think that something that really needs more scientific validation. Well, so that's where the scientific validation comes from. So they're making all these measurements, and as they continue to add more data, the signal becomes stronger. So any individual measurement can have a large uncertainty, but the aggregate measurement the uncertainty gets smaller and smaller and smaller. So while an individual measurement, you can't necessarily shrink the error bars on an individual measurement more than what you already have, because that's just kind of the nature of, that would require, maybe understanding something more than is possible in the universe. But when you make multiple measurements and they all the average shrinks down, then you can get a more precise measurement of the average. It's one of those, the same thing happens with statistics of other things. So if you take, like what is the average class size? So this says average class size, even though it doesn't really look like it, at a high school. Then what you do is like, say that the average class size is 30, but some classes might be like 33, some classes might be like 26, and these are gonna have uncertainties associated with them that are like Poisson distribution or something like that. So you're gonna have, each individual measurement is gonna be something like 30 plus or minus the square root of 30, which is like 5. Okay, so each individual measurement of a class size is gonna be, you're gonna have something near 30, like 25 or 35 or whatever, plus or minus 5. And so it's gonna have error bars that are relatively large, like 20% error bars. It's gonna be 20% error bars. However, as you keep making the measurements, your uncertainty in the average, so this will be, the distribution that you get for each individual measurement is gonna follow this with like 30 plus or minus 5. But as you keep measuring new classes, each individual measurement is going to have the same size error bars, but the uncertainty in this measurement itself is going to shrink as 1 over the number of observations, or 1 over the square root of the number of observations. So you measure 10, then your error bar in the average is going to shrink down. You measure 100, the error bar in the average is going to shrink down even more. And so your uncertainty in the mean, which is the thing that you actually care about, not the individual class that you care about, it's the mean class size, the average class size that you care about. And the uncertainty in the average is going to shrink, even though the uncertainty in any individual measurement does not shrink. And that's what's shown in this figure, is that as they continue to add more measurements, the individual uncertainties stay the same, but the uncertainty in the average shrinks down with the number of observations. And so the ultimate error bars that they're using to make these calculations are shown in these figures. If we zoom way in, and the computer catches up to me. So here is, you can see the average uncertainties are the error bars on the pink points. And those are quite small compared to the distance between the two different models, the dark energy model and the dark energy, like with dark energy solid and without dark energy, the dashed. So that's where it comes from.